Okay, so we're going to take a look at the very last topic of the year, the hyperbola. It's the final and probably the weirdest of the conic sections. It definitely has some very significant applications, but not probably quite at the easier level that some of the other ones are. But the hyperbola, anyway, let's talk about what it is. So the first thing that I wanted to do is show you a picture of Geometer Sketchpad. So what I have done is I've created this little diagram, and it's kind of the same one that I've done in each of the previous videos. This distance from A to B is exactly the same. Let's go ahead and label this point as the distance from A to D. So no matter how I move this thing around, the distance, let's fix this a little bit. The distance from A to D is the same as the distance from A to B, because I simply just took a little perpendicular bisector of this segment right here. And so no matter what, any point on a perpendicular bisector is going to have the same distance from any point on it. So as I move this along, point A is always that same distance. Now, what's interesting is that would mean is that if you took the distance from A to C, right here, and you took the distance from A to B and you subtracted them, well, if this distance, AC, take away AB, well, then always you would end up getting this piece right here, since AD plus DC is the same as, if we substitute that AB in and subtract, you just get this. So the long one minus the short one just leaves this piece. So no matter what, as I move it around, then the difference of all of these things would be DC, but DC is just the radius of that circle, meaning that's a constant. So if I go ahead and animate that or trace those values as I move them along, what's going to happen is it's going to collect all of those. Oh, whoops, I traced the wrong value. Whoops, just kidding. Let's go ahead and let's erase those traces. Turn this one off. I meant to trace this one right here. So these are the places where they would always be the same. So as I move them along like this, notice we are collecting all of those values. And this shape right here is known as a hyperbola. And of course, if we, put the points maybe be a little bit closer in, this is going to change the story quite a lot. I'm making it closer and closer and closer to C. And again, very similar to what we did before. This is going to modify what we would call the eccentricity of the curve. So now you'll notice that based on the pixel size of my screen, we're having a lot of values that if I go really slow, I could pick up more of those values. But ultimately, that's kind of what a hyperbola looks like. So with that in mind, let's go ahead and let's duck over here into Desmos, and let's kind of see what happens in Desmos when we study what a hyperbola actually looks like. So all of the conic sections, as you recall, start with some kind of an x squared plus y squared. Now, of course, if you have x squared plus y squared, plus say 4x plus 8y equals 10. That's going to be our nice little circle. And of course, as we start playing with those, making those numbers ever so slightly different, that makes the ellipse. Remember, if you have an x squared and a y squared and they're both positive but different values, then we have various forms of an ellipse. Again, as you change those numbers, it changes which way it's oriented, etc. If you made one of them 0, it's a parabola. But what I have avoided doing through all of these problems is inputting any kind of negatives. Now, as soon as I put a negative in here, all of a sudden the shape changes. That is now a hyperbola. Now, again, if I make them both negative, some people think that's going to work. But as it turns out, if you make them both negative, that's still an ellipse because I just divide everything by -1. But if one is positive and one is negative, that's going to be our nice little shape, the hyperbola. And they do sort of look like a parabola when you first look at them. This looks like a simple parabola. Like, you know, if you covered half of it up and you were only looking here and you said, what is it? You would probably think it's a parabola. But as it turns out, the more that you scroll out, the more that you realize that that does not at all look like a parabola looks, because these look phenomenally linear. They look pretty interesting, just simple little lines. Now, when you zoom in, they don't look like lines. They look like, you know, like curves, but they actually have asymptotes that are at play. So recalling back in time to what we did recently to the ellipse, if we started off with, say, something like x plus 4 squared divided by, say, 16, and maybe y minus 1 quantity squared over 25 equals 1. See, that is the simple shape called the ellipse. But all we have to do is flip one sign in the middle here, and all of a sudden it becomes a hyperbola. And similar to the hyperbola, the ellipse, it has a center at -4,1. That should not really surprise anybody. And notice the value underneath the x right here. Let me zoom in a little bit so it's not counting by twos. So you'll notice in the x direction, just like we did in the ellipse, let's move over and back 4 units. Now, if I move over and back 4 units, that's going to be at 0, 1. That's going to be one vertex. And if I go back 4, that's -4, 1. That's going to be my other vertex. Very, very similar to what we have done in the previous one. Now, the part that's a little bit different that we're going to see as we come in is like, how do you go ahead and find some of those other pieces? And so we're going to go ahead and get over here into my document camera to go over some of the pieces. So the definition of what makes it what it is, it's all the point in the plane such that the difference. Now, the only word that changes between an ellipse and a hyperbola is instead of using the word sum, it's the difference. And those two fixed points has to be a constant. Remember in that video I was showing you, that was actually the radius of that circle that we did. So here's kind of how I personally like to play the game. So let's look at this guy right here. So it's probably going to be easiest for me to kind of demonstrate all the bells and whistles of this thing through this lens. So I have one here that is an x squared first and one here that's a y squared first. So the first thing to know is you just kind of have to know that anytime you have the x squared as the first one or the positive one, it opens side to side. In other words, in the x direction. Whereas if y is first, it's going to open up and down again in the y direction. So let's just take it from scratch. I think -2, -3 is fairly obvious why we would start here at the center. Let's go ahead and make a little list over here to the side. Let's do the two vertices. Since this opens in the x direction, I'm going to go over 2 and back 2. That's going to be 0, -3. And -4, -3. I'll go over 2 and back 2, simple counting. Now in the ellipse, we would go up 3 and down 3, 1, 2, 3, down 1, 2, 3. Now here's where everything kind of starts to change. What we do is instead of drawing a curve through those points, we go ahead and draw a little quickie box. Now, I made reference in that Desmos piece that it looks kind of linear. Well, the line is actually dictated by this box. So I'm going to go ahead and draw this in here right here. I'm going to draw an X right through the corners and the middle of the box like that. Now, one of the nice things about that, if you kind of follow kind of how that worked, through that box right there, is to make this line, I went up and over, but the up was the 3, the over was the 2, so the slope of this line is 3 over 2. The slope of this line over here is down 3 over 2. Now again, I think I've probably made it pretty clear in here that I really like point slope form. And so all I need is a point and a slope, but the cool thing is it always goes through the center right here. So this line right here would be this guy, would be y minus the y value equals m times x minus the x value. And not on accident, you'll notice the y plus 3 and the x plus 2. They're exactly right there. Notice the rise of 3 and the run of 2. Again, the square roots of those. This line is exactly the same line, except it has the negative slope. And then all we need to do now is sketch the curve, and we're good to go. So it starts here, curves up, looking like it's becoming closer and closer to that asymptote. Remember, a parabola never gets closer to being linear. It just gets steeper and steeper as it moves off to the side. And the only thing that I have not dealt with yet in any way was how do you find the foci? Now, when we had the ellipse, we took these two numbers right here and we actually subtracted them. So all we're going to do now is we're just going to add them. So 4 plus 9 is 13. So my focal distance is going to be root 13. So from the center, I'm going to go over and back root 13, which is just a little bit underneath the number 4. 1, 2, 3, just a little bit under 4. Here's one focus. 1, 2, 3. Just under there, that's 4, that's the other focus. And let's write over here how I would say that. Now, those are not nice numbers, right? So I started at -2, comma, -3, that's the center, and I went to the right root 13, and I went to the left root 13. And that feels like it's like cheating or something, but that's literally what I did. And since these this one is rational and that one's irrational, I really can't combine them unless I make them into a decimal. So that's really pretty much how you graph a hyperbola. So now this one again, let's do the same process. I'm going to go to the left 2 and up 1. In the x direction, I'm going to go over 4. 1, 2, 3, 4. 1, 2, 3, 4. By the way, this axis right here, excuse me, this one right here is known, this line that would go right through the heart of every piece of this, just a little anatomy thing, is called the transverse axis. And the other one that kind of just cuts through and goes through outer space, but actually still has information about the center on it, as well as the rise as part of that asymptote. This one is called the conjugate axis, the other axis. So keep in mind the transverse axis is always going to be the one that goes in the open of direction. So the transverse axis for this one is going to be up and down. This one's going to be the conjugate axis. Now, as it turns out, I'm going to have to go up the square root of 20. Now, keep in mind, root 20, that's 2 times 2 times 5. So that would be 2 roots of 5. So my vertices, so let's write that down, -2, 1. My vertex 1 and 2 would be at -2. And then I'd start at 1 and I'd go up root 20 or 2 roots of 5. And then I'm going to go down 2 roots of 5. Now, the square root of 20 is around 4.5. So 1, 2, 3, 4.5. 1, 2, 3, 4, and about a half. Again, we're going to make ourselves our little box right here. That box is going to help me define my asymptotes. Come in here and we'll draw in our lines. I'm trying to keep the video short. I normally use a straight edge to draw these things, so I'm not guessing at them. I'm doing a pretty decent job at that, but I'd really like to see you use an actual straight edge to make those work. Now, like I said, this one is going to open up and down, so it's going to be over here. You're going to notice that this one's a little bit lazier than the one that I did above. There it goes. Cruises along, touches the box right here, and starts opening in the up direction. This one down here opening in the downward cycle, trying to get closer to that line. Again, the point that they go through is y minus the y value. It's x minus the x value, and then my rise was 2 roots of 5, and my run was 4. Oh, hey, what do you know? I could probably reduce that a little bit. I could make that 1 root of 5 over 2. There we go. And Of course, these two axes have the same exact asymptote. I'm going to fix one little thing that I just realized I missed, is that this line is coming down, so it has a downhill slope and an uphill slope. And I guess the only thing left to do is talking about my foci. Now again, 20 and 16, in this case, remember in the ellipse you subtract, but since there's a minus we're going to add, that makes 36, but the square root of 36, of course, is 6. So from the center, I'm going to go up 1, 2, 3, 4, 5, 6. There's focus 1. 1, 2, 3, 4, 5, 6. There's focus 2. There they are. So again, labeling them, up 6 is 7, and down 6 is -5. I have now thoroughly graphed my hyperbola, and we have literally then just one little piece to go. And that is in the last video, we're going to go ahead and deal with how do you get it into this form right here when it's not, and not a particularly significant piece, just remembered I should mention it, is what is the eccentricity, because that's, again, the measurement of how wild the shape is. So in this case, my eccentricity is C, which we found in the graph to be root 13. That, again, was our focal distance, over A, which is 2. You're going to notice that this number is always bigger than 1. In a hyperbola, it's always below 1. In a parabola, it's equal to 1. And in a hyperbola, it's above 1. So in this case, my eccentricity would be C, which we found to be 6, over A, which was 2 roots of 5, or in other words, this. And again, 3 is a little bit bigger than root 5, and so that's why the eccentricity, again, hyperbola will always be above 1. Hopefully that was not too tough. I'll see you back in class. One more video to go on just, again, fixing the format. All right, we're out.